Hey everyone. I'm using different headset this time, so hopefully you can hear me. It's having some trouble with the other ones, so hopefully these are okay. All right, so I'm gonna go ahead and share my screen so we can actually get started. Today I think we're gonna be reviewing for the exam. And let me switch over to the slideshow and from the beginning. Okay, so today, exam 1 review, we're talking about trees, balanced trees, and heaps, so all the things we talked about so far this semester, okay? All right, let's get started. Okay, so first we're talking about trees and traversals, terminology, types of trees, types of traversals, then binary search tree, insertion, deletion, search, and then pseudocode as well for those. It's good to know that. And then ways of implementation and representation and how they perform, like big O notation. And then balanced trees we're going to talk about as well. AVL trees, red black trees, B and B plus trees, split trees. No pseudocode, but it's important to know the performance and kind of what they do. So we'll talk about those. And then heaps and priority queues. So, well, again, we'll talk about pseudocode here. So again, I think it'll be good to know how to write some code for like trees and traversals and heaps and priority queues, for example. Right. And we'll talk about the properties, how to represent heaps, insertion, deletion, pseudocode, and performance for those as well. Okay, so first, trees and tree traversals. Okay, so tree, again, usually we have like a node class, right, or a struct for trees, like this. So it just has value and a left and right child. So B is like a binary tree, right? So you have nodes where each node has a list or reference to other nodes. So in this case, it's references. You might need a list, for example, if you want an area tree. But there's several types of trees. And some trees we've seen so far are just like general trees, binary search trees, AVL trees, red block trees, blade trees, area trees, B trees, and typical binary trees. Node looks like this. This is like a binary trees node, right? But for example, for an area tree, maybe we would have n nodes, right, instead of just 2. And then, yeah, AVL trees, right, for example, those are trees. We'll talk about those more, but and those are like self-balancing binary trees. And same thing for red, black, display, and B trees. We'll talk about them more later. But okay, just a refresher on what a tree is. So a tree traversal, remember, tree traversal is where we actually go through and like visit each node in the graph or in the tree. And hopefully you know some tree traversals from your project one. So it refers to the process of visiting every node in a tree exactly once. So there are 3 main types of, okay, so you have level order traversals, but then right here, we have 3 other kinds of traversals, right? So pre-order, in-order, and post-order. And they're different in the, remember, pre-order is node first, in-order is nodes in the middle, like, and then post-order is node at the end. So post, like, it means like last, so node is last. Pre is like before, so node is before everything else. And in-order is just like in the middle. But for all of them, left comes before right. So left before right, but then based on whether it's pre, in, or post, node goes somewhere. So that's how I remember it at least. But, yeah. So okay, let's do an example. What are the 3rd nodes we printed out in a post-order traversal of this tree? Well, let's work through it. Remember that for post-order, we have left, right, and node is the end because post, right? Post would mean last, right? So, or after. So we do this, and so we go, okay, we're gonna go left. So we started our route, right? We go left, then we go left, and then when we're at 1, right? We go left, we don't do anything. We go right, we don't do anything, right? There's nothing there, nothing there. So then we actually get to the node. So 1 is our node. So 1 is the first thing in our post-order traversal. So now we have to go back up, right? Because we didn't see anything. Well, 3 have already visited left. So we're good with left. Now we need to go right. So we go right. When we go right, we go to 6. And 6, we go left first. So left, and then later we will go to right and then node. But we go left first, and we see a 4. And at 4, we go left and we go right. There's nothing there, nothing there. So now we visit the node 4. So 4 is our second one. And we're done with 4, so we have to go back up. Well, we've already visited left of 6. Now we need to visit right of 6. So we visit right. And at 7, we try and visit left, we try and visit right, nothing there. So then we visit the node, and the node is 7. So 7 is our third. Right? Because we just asked for the third node. So we get 7. So let's see. And it's 7, right? So hopefully you understand why. And okay, yeah. And we can also talk about the pre and post order and in order traversals. And so for pre-order, right, we get this because it's node and then left, right? So we visit this node, and then we go left, node, and then we go left. Okay, and then we can't go any further, so we go back up. Then we go right is the only choice now. We can go left, and then we go right. So far 8, 3, 1, and then 6, 4, 7. So every single time we try to go left until we can't anymore, and then we have to go back up to where we could go right, and we go right. So the last place now, since we visited the whole left subtree that we can actually go right, which we haven't gone yet because we've gone left, everything on the left subtree, is actually the 8. So you have to go 8. We go, we've already gone left, so then we go to the right. And here we go left, can't. So, oh, sorry, we visit the node 10. We try to go left, we can't, so go right. We visit the node, we go left, 13, and then, yeah, that's it. That's why it looks like this. So for in order, we have left node, right? So it's just go left as far as you can. So 1, right? Left, and then left. And yeah, we have a 1. So then we have to go back up, right? And we've already visited all the left subtree of 3. So now we actually visit 3. Right? Or we note that it's a 3, right? We put that in our traversal because it's left node, right? We visit everything left, so now we have node 3, and now we go right. So we go right, and we have 6. So we go left first, so 4, and then we go back up 6, and then 7. And so far, so good. And then we've already visited all the things left of 8, so we visit 8, and then we go right. And for 10, we've already visited all things left of 10, includes nothing, so we go 10, and we go right. Now we have to go left from 14, we get 13, and then we go back up, we get 14. So that's why we get that in order. And post order is just along the same lines as we were talking about before when we were drawing it out. Okay. So for binary search tree operations, there's search. And search, when you search for an element in a BST, use comparison to determine if you should continue search through the left or right subtrees of the current node. So what would the time complexity of this be in the average case, and then also like in the worst case? Well, we'll see that after the code. So first we look at the code, but you can still answer those questions. So the base case is, right, if you're at the root, the root is null, so you're actually at a null, you're a leaf, basically. Or a key is present at the root, and then like, or you found it. So you either found it or you reached the leaf, and like, or you went past all the leaves, right? But if it's the key is greater than, then you have to go to the right, right? And if it's less than, you go to the left. Okay. And so yeah, I guess the pseudocode is of course good to know. Like, kind of have an idea. But okay, average, as we said, we wanted to know that. So it's log n, right? Because on average, right, we're expecting a binary search tree to be like balanced, relatively speaking. But in the worst case, it's not balanced, and you just have like a linked list, and that's worst case ON. For insert, when you insert, you again decide left to right where you want to insert, and this is the code for it. And again, if you have reached a null node, then like if it's empty in this case, right, you just return a new node. But otherwise, you go down the tree. So if it's less than, you go to the left. If it's greater than, you go to the right. And then, yeah, so it's similar to search because you have to find where to put it, basically. So of course, it's going to be similar to search, but at the end, you actually have to insert it. And then, okay, that's for insert. And well, I guess I kind of gave it away. But like, what do you think the average and worst case are here? As I said, it's similar to search. You have to find it. And then insert is just a 1, but finding where to go is log n, right? In the average case for the tree. But worst case is still ON, because you might, again, have like a linked list where you have to go through everything. Okay, well, this next one is delete. And you can already see average and worst case, but hopefully it kind of makes sense why. Because with a delete, you have to delete an element by using comparisons to find where it goes. Yeah, so where you place it, right? Because the thing is that for this, it depends on how many children you have. Like you're trying to find like the in-order predecessor, in-order successor that you want to replace it with. In this case, it looks like we're looking for the in-order successor in this, right? Because if it has no children, you can just delete it in a regular BST. But I mean, if it has children, you can't just like delete the node because it has things still there. So you have to like replace it with the in-order successor, swap it with like the in-order successor, in-order predecessor. And then once it's swapped, you can delete it from the tree, right? But yeah, if it only has one child or no children, then you can just replace it, right? Okay, cool. So that's this. That's kind of the pseudocode. Hopefully it makes sense. And so because of that, actually finding the in-order successor, in-order predecessor, I mean, you're basically just searching through the tree, right? And actually finding the node to delete, you're still searching through the tree. And actually deleting it, when you delete it, it's going to be a leaf because if you swap like with the in-order successor, in-order predecessor, it's going to be a leaf. So you swap and now it's a leaf, and removing a leaf is just O1. So it's O1 plus log n average, or O1 plus O1 worst. So that's why we get the worst average we do. So hopefully that made sense. And if it didn't, of course, like, just message me. I want to make sure that you guys get this. Okay, cool. So balance trees. So now we're talking about AVL trees. So hopefully everyone knows AVL trees, and hopefully it gives none of you nightmares. But yeah, it's a self-balancing binary search tree. Balance factors for all the nodes should be magnitude less than 2, so negative 1, 0, 1, right? And the balance factor is the height of left minus height of right. That stays balanced, the insertion, deletion, and searching are all log in the worst case, which is good, right? That's why, I mean, we're never going to have anything with like a linked list of like size greater than like 2 because we're guaranteed that it's balanced, right? Because it's self-balancing. So we don't end up with all the nodes on one side of the tree, for example. So that's really good. So because it stays balanced, we're always assured of this. Insertion, deletion, and searching are log n. Side of the tree is log n. Balance factors are checked after each insertion, deletion, and if needed, the tree is going to be rebalanced with rotations, right? So we might need to balance it again, but it's like it's similar to regular binary search trees, but then we do the balancing, we do the we check the balance factors and do the rotations. So if we insert a 5 into this, what's the tree going to look like? Or what's the root going to be? And what's the tree going to look like? So we insert a 5. First of all, I mean, you start with just a regular binary search tree insertion. So we know, like, where's it going to go? It's less than 10. It's less than 6, but greater than 4, right? So, okay, that's just how we find where it goes originally. Not too bad. But now we have to check. Is 5 imbalanced? No. 4 imbalanced? No. 6 is not imbalanced either because, like, it's negative 1. Oh, yeah, negative 1. Oh, sorry, it's left minus right. So there's just 1. This is negative 1. And then is 10 imbalanced? It is, right? Because left is now 2 greater than right. So now we have a problem. So we have to do a rotation, right? So we have to do a rotation. What kind of rotation do we have to do? Well, we have to do it around, well, 6 is fine, right? 4 is fine. We need around 10. Yeah, so let's see. Or wait, no. Okay, well, we insert 5. No 10 is imbalanced, yeah. So we need to do a rotation. So what's, okay, so you have questions for ourselves. What's the new root going to be, right? Which of these? So that's a poll question for you guys. And then after the rotation, where will 8 be in relation to the new root? Okay, so when we do a rotation, right, we do have to like rotate it so that we change the tree, right? So Yeah. So when we rotate it, first, yeah, we trace the imbalance, we find it's a 10. We go left, left, and we do have to do a right rotation. And the way we know it's a left, left is because the imbalance is left, left from 10, right? It's left and left. Okay, but for a left, left rotation, we do a right, or left, left imbalance, we do a right rotation, which makes sense. Like if you think about it, you're like rotating 6 around clockwise or right. So we do that. And yeah, that's how clockwise. Okay, just thinking. Okay, but yeah, we do this, right? And hopefully kind of see how that works and why that's the case, right? Because it's left and left. And when we do it, this is what we get. And the change we have to make, of course, is like 6's right child now has to be the 10, right? So this 8, or the right child of 6 originally, is now, we know it's smaller than 10. So it can become the left child of 10, right? Because it's on the left subtree of 10. So we already know it's smaller. So that's why this whole right subtree can become the left subtree of the right child of 6. And as we see, left child of the right subtree. So that's the answer to the other question if we go back. So it's the roots right, left grandchild. And what's the new root? It's 6, right? Okay, cool. And there we go. So that made sense. Okay. Now, with our black trees, it's important to know kind of what they are, I guess. Or it's good to know what they are. Like, obviously, you don't have to know how to write code for it, but it's good to know a little about them. So it's an alternative to AVL trees. Yeah, C++ map is actually uses red black trees. They're using scheduling algorithms. They're actually really, really helpful. I think Java's tree map uses them too, because C++ map is like a sorted map, and same thing is true for like Java tree map. But okay, for the black trees, yeah, they're really useful. And in practice, they're a little bit faster than AVL trees, but AVL trees and them are both log n for all insertion, deletion, and search. So binary tree, yeah, it's a binary tree that uses 4 rules, right? These are important rules to remember, I guess. Like to know whether a black tree is valid, it has to follow these 4. You always have to have a node red or black, the root's always black, and a red node always has black children. So a red node cannot have red children. Black nodes can have either a black child or a red child, but red cannot have a red child. And no references are just considered to be black for simplicity for us. And then that way we can have red as a leaf, right? And the number of black nodes in any path from root to leaf is always the same. So that's an important one, like because that's what allows us to be red black tree. Yeah. Okay. So these 4 rules. So if I give you these questions, true or false, red black trees are self-balancing binary search trees. It's true or false. And there are a couple more. But hopefully you kind of figure that out. Okay, the next one is nodes in a red black tree have 1 color. This color cannot be reassigned. Is that true or false? And also the number of red nodes on any path from root to leaf is always the same. So go ahead and try and answer those. You can pause. Okay, so let's go over the answers. So red black trees are self-balancing. I mean, yeah, that's exactly what they are, right? Nodes in a red black tree have 1 color. That is true, but they cannot be reassigned. That's false. Like you have to reassign colors. That's how red black trees work. That's what allows them to have the same number of black on any path from root to leaf. And I mean, otherwise it just wouldn't work. And the number of red nodes on any path from root to leaf is always the same. That is false. It's the number of black nodes. So let's go over the answers. I guess the answer should be here. Right, the first one's true. That's exactly what they are. Next one's false. The color of nodes can be changed if there's rebalancing. So if they balance, you might have to change the nodes colors. And if the number of red nodes is not true, it's the number of black nodes. That's the same on any path from leaf. Okay. Next, B trees. So with the B tree, yeah, a B tree is a tree in which you insert, right? Okay, well, we'll talk a little bit about it, but Like, okay, we'll talk. But yeah. It's a self-balancing tree structure. You store a lot of data for fast query and retrieval. That's what it's designed for. They can have multiple key value pairs in a node. They're sorted descendingly, by keys. It's an n-area tree, has up to n children, and important properties are all nodes have at most n children. The root is a leaf or has somewhere between 2 and n children. And internal or non-leaf nodes have ceiling of n over 2 to n children. So they have no fewer than that, right? No fewer than ceiling of n over 2, and at most n. And then non-leaf or internal nodes have a maximum of n minus 1 keys. And this allows us to know that it's like not going to be just like a linked list, right? Because they can only, like, for example, if n is very large, then each of the nodes actually has a fair number of keys. And yeah, non-leaf or internal nodes have maximum n minus 1 keys. So, and L is the maximum number of keys items a node can have. Okay, so I guess like if we were to insert into a B tree, I guess I didn't go over this much when we actually went over B trees, but what happens is like if I were to insert into, let's say, I don't know, like let's say I insert into a B tree that looks like this, right? Where it's like, I don't know, or let's say 2 and let's call this 8. And if I have like, well, I guess it's kind of messy, but whatever, 3 and 4, and let's say just 9, or whatever, and then, I don't know, 1, then, I mean, the important thing is that like when you insert into it, like let's say that the most number of keys anything can have is 3, right? Then when you insert into it, it'll take, like for example, if I put a 5 here, it'll take the middle one and move it up into this. So I'll have something like 4 here, and it'll split them. And the way it splits them is now like if the most we could have is 2, this is going to be split up even more. So we'll have something like this where it's 4, and then it'll have children of 2 and 8, and 2 will get children of 1 and 3, and 8 will have children of 4 and 9. And so the idea of B tree is like you split upwards and you take the middle element. When you take the middle element, like if it's full, right? If a node is full, you take the middle element and you move it up, and the other ones are like its children, right? Okay. I just wanted to go over that because, like, I don't know if I went over it enough last time, so just to see. But that's not the most important thing. I think the most important thing is like this stuff. I just wanted to go over that, but again, I think like just knowing this is more important, and like knowing how to do a question like we'll get to in a second will be more important. But I just wanted to mention that just in case you need to know for any reason. But again, not as important as just knowing what it is. But a B plus tree is a B tree, but each non-leaf node contains only keys, not pairs of key values. And all data is stored in the leaves. So there's no data stored in the tree itself. Everything is stored in the leaves only. Like there is data stored, it's just not the data that we need, right? Like there's a 6 here, obviously that's some form of data, but that's not like all things that we've inserted are only going to be in the leaves. Like we don't know about the rest of the tree. And yeah, an additional level is added at the bottom with linked list. So its entire thing it leaves is linked list. It's pretty cool. Okay, so this is more along the lines of like I guess what's probably more important to know about B trees and what I mentioned. I just wanted to like walk through it so you guys would see because I think it was similar to a quiz question what I did earlier, but this is probably more important. So if you're given a perfect B tree with n equals 3, L equals 3, and height 2, how many unique keys are there in the tree? Well, n is the maximum children, and it can have an L as the maximum number of keys. So you can try and figure this out. And you can pause or whatever. Okay, so let's go over it. So height is 2, right, with 3 levels. And it's 3, right? So we know that the most you can have, it's perfect, right? But even though it's perfect, the most keys we can have as something that's not a leaf is n minus 1. So we have 2 here. This thing has 3 children. I guess L is 3, right? Or sorry, n is 3. Yeah. Maximum number of keys you can have is L minus 1. So not n minus 1, it's L minus 1. But here it has, again, these are not leaves, right? We know they're not leaves because you can only have L minus 1 here. And the reason why we only have 2 instead of 3 here is because you can only have L minus 1, right? Here, unless you're a leaf, and then you can have all the keys you want. But each of these have 3 as well. And those 3 are all leaves, right? All these guys are leaves. And they can, which means they can have up to L values. So that's 3, 6, 9. I'm just summing. They would each have 3. I'm just adding as we go. 12, 15, 18, 21. Okay, you get 24, 27, 26, 28, 30, 32. I think I missed something. Oh yeah, sorry, 24, 27, 29, 31, 33, 35. Yeah, I just missed this 3 here. I should have written all the way out. But yeah, it's 27, right? Because 3 by 9. And then 2 by 3. So we add those and then 2 by 1. So we end up with 35. Okay. And now we see the reason why. Level 0, there's 1 node, each with 2 keys. Level 1, there's 3 nodes, each with 2 keys. So that's 6. And then at the leaf, right, you have 3 by 3 by 3. So that's 27. Yeah, so all nodes have at most n children, and non-leaves have up to n minus 1 keys. Yeah. And I guess this n, well, L is the maximum number of keys a node can have. So I guess this n is the L, but yeah. Okay. Cool. So, all right, so moving on. Okay. So for this one, we can see a drawing. And 2, 2, 2, 2, and 3, 3. So it's a better drawing than I had, but you get the idea. So non-leaf nodes have up to m keys. So we see that again. Okay. So how would the problem change? What would the solution be? Well, how would the problem change if we had a B plus tree instead of a B tree? Okay. Well, for a B plus tree, you can pause and think about it. Okay. For a B plus tree, remember the difference is that for a B plus tree, the internal nodes do not store data. Like they don't store actual keys. So as a result, all of it's still like the same as the B tree. It's going to look the same, except instead of with the B tree in which at the leaves, instead of a B tree where the keys come from all 3 levels, with the B plus tree, the leaves are the only one with the keys that we care about. So if we actually look back, well, how many keys are there at the leaves? We'll give us the answer here. Well, 3, 6, 9, 12, 15, 18, 21, 24, 27. It's just 27 because we don't have keys here, but otherwise it's exactly the same. Oh, besides it being a linked list, but that doesn't apply to this question. So it's just 27, right? And that's it. So if you see a visual representation, this is the only place keys are actually, like data is actually stored for the keys. Okay. Because it's unique keys, so these may not be, or these won't be unique values because of this. But anyway, now we'll talk about splay trees. So for splay trees, they're also self-balancing binary search trees. And after a node is accessed, it moves to the root via zigzag rotation. So it looks like this if we just accessed a 1, right? And it's best for ensuring that commonly accessed nodes have the least access time. So what is the last node that's accessed in this splay tree? Well, the way we figure that out is, you can try and pause and figure it out. Okay, the way we figure that out is we just look. We look at the split tree, and we're like, okay, what's the root? 5. 5's the root. So that's our answer. Because, yeah, for a split tree, it's just the root is the one that you access last because it moves up to the root. Like if I was down there before, it moves up the tree. So it's most recently, it's just whatever the root is after the rotations. So, okay, so heaps and priority queues. So priority queue is a special type of queue in which each element is assigned a priority. An element is with high priority is dequeued before an element with low priority. So we prioritize things with more priority. Yeah. So if two elements have the same priority, they're served according to the order in the queue. So that's just like a tiebreaker criteria. Functions. So the main functions of priority queue, and it's just reviewing what we already know from previous discussion. Insert, peak. So that's just looking at whatever's like the, yeah, when you peak, like you can only see one element, which is the root, if we think of it as a tree representation. Pop highest priority, so just get rid of the root if we think of it as a tree, right? And it may have the same operations for lowest priority, but it depends on the implementation. And it may not, so yeah. But in general, when we think of priority queues, it's just either lowest priority or highest priority, you know? Yeah, that we remove. So if our priority queue with like numbers, right, maybe, I mean, we'll sort them based on how large they are. Then the highest priority will be with higher, larger numbers, right? Okay, so binary heap is a heap that has like 2 children each, right? Like every node has 2 children. So it's a complete binary tree that satisfies the heap ordering property. So it's just a priority queue. The priority queue is just a heap. And when referencing a node in a binary heap, all of its children are either less than it or greater than it. So it's like we order by levels almost, right? So like anything below me is of less priority. So if we want something, everything less than it to be below it, that's a max heap because I'm larger than everything below me. And if we want all of my children to be greater than me, right, then I must be smaller than all my children, and all my ancestors, or not my ancestors, like the people who come later than me, right? And these are that's a mini, right? Because I'm smaller, but I'm above them in the tree. So the root is the smallest element in a min heap and the largest element in a max heap. And that's an important distinction here. This next thing about heaps is that you can only remove either the max or the min, depending on what kind of heap it is. So if it's a max heap, you can only remove the max, and if it's a min heap, you can only extract the min. And yeah, so removing it is only a 1, but then to actually run heapify to get it back to the property of a valid heap, that's a login. So the whole thing is a login. And the way it's done is so for insert, right, you insert at the end of the heap and then just heapify your way up. And this is a complete binary tree. It's balanced, like it's not necessarily balanced, but it's complete. The height is only log n. Okay. So example min. Oh, okay. I guess it is. It's balanced. It just, yeah, it doesn't have the same properties as like an AVL tree, for example. But it is balanced. So yeah, it's complete. Okay. So a heap data structure. You have a min heap and a max heap, for example, here. Okay. So usually we use array representations because it's just a lot easier to work with. So we think of the root node I is 0. Binary heaps are implemented using an array for any node at index I. The left child, if we do left child is 2i plus 1, and right child is 2i plus 2. And then we can just go do the reverse to figure out what his parent is. So the parent is just I minus 1 over 2. Right. And for 0 index is even nicer than 1 or 1 index is even nicer than 2 index, but both work. Yeah. So yeah. And using this representation is very easy to figure out like who your parents are and who your children are. And so it's easy to run like heapify and yeah. Okay, so question number 6. What's the array representation of the following heap? Okay, well, let's figure this out. So clearly 88 is the root, right? And the root's gonna come first. So 88. Then our left child is 2i plus 1, and our right child is 2i plus 2. So it's 0 times 2 plus 1, and 0 times 2 plus 2. So we have 66 and 77. Okay. And then now from position 1, we have 2i plus 1 is 3, and 2i plus 2 is 4. So now we have its children, 33 and 44. And then we can look at the next one. 2 times 2 plus 1, because it's position 2. So that's 5 and 6, right? So 0, 1, 2, 3, 4, 5 is the next thing. So its children, 55 and 75. And we can actually just keep going with this. So now that we have these children, now we look at 33. Left child of it is going to go next. We're just following the same pattern. But if we want to do this, right, it's 0, 1, 2, 3. So 3 times 2 plus 1, 7. So 30 is going to go in position 7. 22 is going to go in position 8, and so on. And okay, we only have one left, so let's just do it. It's 5 is here because 44 is the left child of 44. And that's position 5 times 2 plus 1 is 11, right? Position 11. So if we look at it like this, I think the answer is just A. Okay? Yeah, there we go. So question number 7, if the insert operation on a heap, well, in the insert operation on a heap, where's the node initially inserted? And this is before we call heapify or whatever. Where is it inserted? Okay, so you can pause. We'll go over the answer now. And the answer is it's not at the top, and it's not as a child to the root, and it's not anywhere. It doesn't matter because we want to keep consistent with what we do, so it's a lot easier to write the code for. Yeah, just the next bottom right leaf. Because we insert at the end, and then we just heapify up. So heap insertion, let's go through some of the code and talk about it, right? So, I mean, yeah, it's good to know the code for this stuff. So yeah, for insert node, if the heap size is 0, you can just insert it at the last element, which is this first element. And, I mean, it's the same and you're done, right? But if it's not 0, which is the general case, it is in the general case not going to be 0, you just insert at the end. You might have to increase the size of the heap. You insert at the end, and then you just percolate up or heapify up. It's percolate up or heapify up. They mean the same thing. And yeah, you just put the position that it's in, heap size -1, right? The heap size of the heap and the heap itself. In this case, what we're calling, right? So, okay. Let's look at that. If we want to add 1, we add 1 to the end of the array. And this is a mini heap, if you'll notice, because the smallest element originally was the root. But okay, we insert a 1. And let's just keep going through this. So in this case, because obviously the heap was not empty before we inserted the 1, so we're not in the if statement. Increase the heap size, and then call heapify up. And for heapify up, let's look at the code for that. Heapify up, we have a parent, or you find the parent, right? It's child -1/2. If heap child is less than heap parent, so we're checking if 1 is less than 12. If it is, we swap them, and then just heapify up from there. Well, is it smaller? It is, so we swap them. And yeah, we're just calculating where the parent is, and if it's less than the parent, we just swap. So that's the nice thing about heaps, right? Makes sense. It's not like as confusing as like AVL trees with the rotation and stuff. Okay. And then now the 12 is in the right place because it's less than 1. But okay, now 1, we check against the parent, its parent, which now is 5. So you swap because it is smaller. You swap them, And now you try call heapify up again. We'll notice we can't because it's already at the root, right? Yeah, like the parent is null, so we're done, right? So that's how that worked for insertion. Okay, so yeah, if in the delete operation of a heap, which node is always deleted? You pause, try and answer. So the important thing to remember is that in a heap, whether it's a min heap or a max heap, the only thing we can do in a min heap is extract min. The only thing we can do in a max heap is extract max. So all we're ever doing is removing the root. That's it, like, or the value at the root. And it's the root, right? Like, so that's the thing about heaps is like they're useful, but that like the only thing we know about heaps is that the smallest element in a min heap is at the top and the largest element in a min heap or in a max heap is at the top. So the only thing we can know to delete is the root, right? Okay. So moving on. So heap deletion. So we start with the max heap. And with a max heap, we'll just look at the max heap case here. We have delete node, right? And so for delete node, if heap size is 0, then we return, right? Because there's nothing to delete. But otherwise, as we said before, the thing we're deleting is the root. So in the case we want to remove the root, all we really do is we just say, okay, we'll get rid of it. And we just say, let's just swap the last element and the first element. And that essentially deletes it because we're decreasing the size of the heap. So in this case, we're going to remove 66. So we put the 12 in where 66 is, put 12 here. And if we decrease the size of the heap, which means we like get rid of this by decreasing the size of the heap, right? Then essentially we've deleted 66. So then we call heapify down or percolate down. Again, they mean the same thing. So for heapify down, okay, so first let's go through delete node. So heap 0 is the last element in the heap, which in this case is 12. Decrease size of the heap, basically just remove that the other 12 which was there and heapify down. Okay, so for heapify down, a lot of we look at the left and we look at the right. And again, these are easy to calculate, right? We just calculate the children. And if the right is, we just basically want to find the max of this, right or left. And the max in this case is the left. So that's all this code is doing. We're trying the left. And if the max in x1 is the parent or is this itself, then we're done. But if it's not, then we have to do a swap. So we swap the largest. In this case, we swap 12 and 45 because largest was left. So we go through it. We have max index becomes left, right? And if the max index is clear, not the parent, so we actually swap them. So now we call heapify down again. And in this case, we actually get the max index is the parent because 12 is greater than 10 is greater than 5. So no swaps, and we're done. So delete node is the same for min and max heap. Is you just, obviously, if it's empty, you can't delete anything, right? There's nothing to delete. But if there is something to delete, then heap size is, like you set the first element to, like you grab the last element in the heap and put it at the root, decrease the size of the heap overall, and call heapify down. And heapify down here, as you can see, is just like getting, in this case, it was getting the 12 into the right position because obviously it shouldn't be at the root. Well, maybe it should have been at the root, but in this case, clearly it shouldn't have been at the root because it wasn't smaller than both these. So we just move it down until it gets the right spot. And then for heapify down or percolate down, it's, yeah, just flip these less than or greater than signs for min heap because we want to find the smallest, but for a max heap, it's greater than. So all we do for heapify is we get the left child, we get the right child, and we get our current position. And if the left and right are both in a max heap, I guess, in a max heap, if the left and right are both smaller than our current one, we don't need a swap. But if they're great, if one of them is greater than, we get the largest of them. We want the largest because, like, let's say we have like x, y, and z, And if we know that z is like the largest of x and y, then clearly moving it up to the here, right, and x down is fine, because we already know that if it's the largest of these three, it's larger than y and x. So that's why we did it that way. And we just get the largest of the three and move it to where like our x was in that case. And the other two are the children. And then we keep going down with x until we get to where it should go. So then we just call heap down again if we actually make a swap. But if we don't, we're done. Okay. So heap performance. So what's the worst case time complexity of adding or deleting from a heap? And you can stop and think about it. Or if you're here, then you can also answer if you know the answer. Or if you don't. Okay. So with a heap, remember, it's a complete binary tree. And so what we know is that since it's a complete binary tree, when you add or you delete, whether it's heapify down or heapify up, the most elements you're going to have to go through is the height of the tree, right? Because like for adding, you have to add it to the end and then just heapify up. The furthest you can possibly go is to the root. And for deleting, you call heapify down, and the furthest you can possibly go is from root to leaf. And that path is only log n. It is only log n because the height of it is only log n because it's a complete binary tree. So as a result, worst case time complexity of that is just log n. Okay. So for an array with n elements, what would be the time complexity of building a heap based on inserting all the n elements of the array into a new heap? So suppose we had, basically what it's saying is, suppose we had a heap, right? And we wanted to then move all those elements to a new heap via the normal heap operations. So like we wanted to delete, or we wanted to extract elements from the original heap and then insert them into the new heap. So if we did that for all the elements, what would be the time complexity? Well, okay, so to build a heap, we know is only n, but the problem is that in order to insert all the elements into a new heap, what we're gonna have to do, right, is if we already have an array with n elements, we have to actually like extract each one by one, right? And so that means that each time we want to get an element from our original heap, that takes log n time. So we have to extract, or log n time just to remove one. But we want to remove n of them, we have to remove log n, but n times, so n log n. And then we just can add on the fact that building the new heap is just n, right? But this is just like big O of log n, or big O of n log n, rather. So that's why we get B. Yeah. Total time taken will be n times the complexity of adding a single element to the heap. Okay. Yeah, if we consider removing as well. I mean, building a heap by itself is still only O(n). But if we were actually using like, if we're using the regular insert and like, yeah, then in general insert is log n. Yeah. So it's n log n. Okay. I think that's it. Yeah. So if you guys have any questions, of course, just message me on Slack, or if you're here, you can ask me a question. No, I think that's it. Thanks, everyone.